Welcome back to our Structural Engineering Vibration series. In this lesson, we dive into the spring mass model, a fundamental concept in vibration analysis. Imagine an airplane touching down on a runway. The moment the landing gear hits the ground, it compresses, absorbing the impact and preventing a rough landing. But what happens next? The landing gear doesn't just stop. It bounces up and down before settling. This is because it behaves like a spring mass system, a fundamental concept in vibration analysis. When an airplane lands, the struts in the landing gear act like springs, storing potential energy as they compress. This energy then converts into kinetic energy as the struts extend back to their original position, causing oscillations. What controls these vibrations? The stiffness K of the landing gear strut, the mass M of the aircraft, the force, F, acting on the system. To predict how an aircraft's landing gear will behave, engineers use the spring mass model. The same model we'll analyze today. Let's simplify this idea with a basic mechanical system, a mass attached to a spring. What forces act on the mass? Gravity pulls the mass down. Spring force pulls the mass back up. Hooke's law tells us that the force applied by the spring is proportional to its displacement. This equation tells us that when we stretch or compress a spring, it tries to return to its original position. But how does this lead to vibration? The parameter K is known as the stiffness of the spring, a fundamental property that defines how resistant the spring is to deformation. The relationship between the spring force and displacement can be either linear or nonlinear, depending on the range of motion. However, we focus on the linear case. Now that we understand the basics of the spring mass system, let's analyze its motion by setting up a free body diagram and solving the equation of motion. Let's consider a massless spring with a mass attached at its end. The system is initially at rest, in its equilibrium position. But when the mass is displaced, the system experiences forces that cause oscillations. The mass of the object is denoted as m. The stiffness of the spring is K. The mass moves on a frictionless surface along the x direction, meaning no external resistive forces are present. The only force acting on the mass in the x direction is the spring's restoring force, given by Hooke's law. The force opposes the displacement. The farther the mass moves, the stronger the spring pulls it back toward equilibrium. By applying Newton's second law, which states that the sum of forces equals mass times acceleration, we get this relation. Rearranging, we obtain the standard form of the equation of motion for a simple spring mass system. This equation describes how the system moves over time, with acceleration being proportional to displacement but in the opposite direction, causing oscillations. From physical observation, we know that systems like springs and pendulums follow periodic motion, meaning their movement repeats over time. A function that naturally describes oscillation is the sine function. So let's assume the displacement x of t follows this form. To verify that this is a valid solution, we need to differentiate it. Differentiating x of t once gives us the velocity. Differentiating again gives acceleration. Now, let's substitute this into our equation of motion to check if it holds, factoring out this term, since it's never zero. Solving the equation, we obtain the system's natural frequency, the rate at which the system oscillates when disturbed. Since our equation of motion is second order, it has two unknown constants. These are determined by the system's initial displacement and initial velocity. Solving for a and phi, we obtain these constants. This means that the system's behavior is fully defined by its natural frequency, initial displacement, and velocity. Now, we can write the full equation for the motion of the system like this. This function completely describes the motion of the system, predicting how the mass moves over time based on its initial position and velocity. To summarize, this is the equation of motion. The solution is sinusoidal. We found the natural frequency. Amplitude and phase are determined by initial conditions. In our next video, we'll explore harmonic motion and viscous damping, key to controlling oscillations in engineering. Remember, vibration is everywhere, from aircraft landing gear to a kangaroo's leap. But think, where else do you see these principles in nature? Physics is all around us. Like, share, and subscribe for more. See you in the next lesson.